right now we want to talk about the pole placement design, and therefore let's just imagine a system described in state space. We therefore can write the following state space equations. Plus b times u, and then we can say the output equals z times x, for instance. We ignore the d term, and then we say, okay, what is our steering vector u, and we say we let u be it's minus k times x, and this k will be named the so-called gain matrix. That's this one. And what we are talking about now will be, can we design this gain matrix in a way that we can enforce our system to be controllable? And the easy answer is yes, we can. And that's what we do in pole placement design. So our aim is the following. We will write this down. We will design the state feedback. Gain matrix. In that way, that the closed loop poles can be chosen freely. Okay, and from the other videos we already know that the poles correspond to the stability of a system. So whether we can put them on the left side of our diagram from the imaginary and the real part of the transfer matrix. And yes, that's why we want to place those poles to a location that we desire. And right now we will do the following. We will start with some given poles. And we will call them lambda I. And we say, okay, we need our system to have those poles to be stable and controllable. And now we will derive this gain matrix K in that way that the overall system will have those poles. Okay, what will we do? First of all, we define our closed loop system. The closed loop system will be slightly different from this system. We will say x dot equals the original A minus B times K, and this whole expression times X. That's what we need right now. And then we can derive from this expression a whole eigenvalue problem with the eigenvalues lambda. So the poles will be the eigenvalues, and the eigenvectors v. So those are eigenvalues. And then we will need some vi, and those are the eigenvectors of this expression. And then we can write the eigenvalue problem in the following form. No problem. A minus lambda I times the identity matrix I, semicolon, minus B, this is one matrix, times the following matrix, the eigenvalues V, and an expression K times V. And this shall equal 0. Alright. From this expression we will get the expressions for VE as one part and the product of K times VE as one product of the expression. And we afterwards have to calculate this K out of this expression. Okay, right now we can modify this line to the following form. We will use the null space description and say A minus lambda E times identity matrix semicolon minus B. So, and this shall equal a vector combination of E1 and E2, and they are not the same because we say that between them there is a correlation, and we call them V and K times V. This equals some correlation coefficients alpha 1 E1 and plus alpha 2 E2, and there's the correlation, and those alphas, they are a design decision. So, and then we can calculate our K out of this, and we can say K equals this product that we have in here. So K times V E times VE to the power of -1. Yes. And then we have derived this closed loop feedback gain matrix K, with what we can say whether or whether we can enforce the system to be controllable or not. And what you find in the exercise in the lecture description is exactly such a system, and you will see an open loop system that when we plot it in the step plot will be kind of unstable. So, and when we introduce this K and close the loop, we will enforce the system to be stable. So you will be able to see that in the script as well. Okay, thanks a lot.